All right, so let's do the next step. The next step is we would like to simplify the Navier-Stokes equation. Okay, so so far we have postulated the solution, and then we tested postulated solution really satisfies the continuity equation. So they are good candidate. Okay, so okay, let me just rewrite the postulated solution here. Is the following. In this case, what we have here is the u equals to u of the y. V equals to 0 and w equals to 0. Okay, so now we would like to use this, the u v w to simplify this Navier-Stokes equation. Okay, so to do this, okay, let's just we can actually start taking a look at each terms here. Okay, so the maybe the easier is the v and w, because this v and w is the both 0, right? So for example, if you take out the if you take a look at the left hand side of this equation, by the way, this is what is shown here is the xyz Navier-Stokes equation in the Cartesian coordinate. So in this case, okay, because v equals to 0, we are able to say this term equals to 0, this term equals to 0, this term equals to 0, and this term equals to 0, without any the ambiguity here. Okay, because the w also equals to 0, this is also 0. This w is also 0, right? Okay, so it's not bad. Okay, they have been cleaned. Okay, we can also take a look at the following. Okay, this u is u of the y, so it only depends on y. Okay, so if you take a partial derivative of if you take a partial derivative of the u, then this entire things must be equals to 0. And then if you take a look at anything, okay, du dx also this one equals to 0. Du dz equals to 0. Okay, so potentially this du dy term, this du dy may or may not be 0. Okay, however, because we have this v equals to 0. Okay, so therefore it equals to 0. Okay, so this is the after this analysis, right? After this analysis, this is very nice. In fact, what we found here is the everything on the left hand side of this equation equals to 0. Okay, so let's take a look at the right hand side of the equation. Okay, in this case we can do the same thing. Okay, this is the velocity also. This velocity equals to 0. Velocity of the v, okay, y component of the velocity equals to 0. And then z component of the velocity also equals to 0. Okay, so all of this is the equals to 0. We can also take a look at this u. Okay, u is the u of the y. So this part, right? Of course, this equals to 0, and then du dz also equals to 0. The only non-zero term that you may have is this viscous term, d square u dy square, because u depends on y, so this is really a term here. Okay, right. So this is great. Because of this, the postulate for the flow, okay, flow velocity, it really helps to simplify this equation a lot. Okay, so let's do a bit of the further simplification here. In addition to this, okay, we can also think about the gravity here. Okay, the simplification with the different the conditions. Okay, so let's consider the gravity. So in our if you remember this is we said there is a two plate. Okay, two plate here. This is the side. Okay, this is really the side view. Okay, this is the side view here, right? And then we said this direction is the y. So in this case, the gravity is acting in the negative y. Okay, so So this is really telling you gx, there is no gravity. Okay, and then also g of the is no gravity. Please don't be tricked because this is not even a trick. You have to see the geometry properly. But just because how we set the coordinate, there is no gravitational the acceleration in the z direction. However, if you take a look at this the y, it is pointing to the negative y direction, right? So what we can say here is the gy equals to minus g. Okay, so this is the point I want to make here is the gravity is in the negative y direction. Okay, so this is great. It's pretty nice, right? So in fact, that's second part. So something that we can do further here is this gx equals to 0, and then gz equals to 0, and then this gy is non-zero, and then this one equals to minus g. Okay, that is the second term. Okay. So this is all right. Then what about the pressure? Okay. This is the pressure. Okay. So this pressure part, we just need a bit of the expression, a little bit of the explanation. Okay. So in this case, we assumed, okay, pressure. As far as this pressure goes, right? Okay. What we can say here is in the Couette flow. Flow is only flow is only driven by the wall. Okay, so it really no component. This really tells you the no pressure gradient in the direction of the flow. Okay, so the direction of the flow that we have in this particular system is this is the x direction. Okay, so this this argument really tells us that the pressure gradient along the x dp dx must be equals to 0. Okay, so this is something that we have here further. Okay, so this pressure part here, dpdx part is the coming from the definition of the Couette flow. In Couette flow, flow is only driven by the wall. Therefore no pressure gradient here. So this is also telling you this quantity equals to 0. Hey, so in fact, so we started with a very super bulky, right? Very bulky in Navier-Stokes equation, but it doesn't look as bad as now, right? So what you can take here is let's try to just simplify this equation. So I'm going to rewrite here. You can go down. Okay, we can squeeze a little bit, and then here. So this is the overall that the everything can be simplified quite a bit. Okay. Overall, what we have here is in the x direction, which is the first equation, left-hand side is equals to 0. And then right-hand side is the gravity equal to 0, pressure equal to 0. And then one term that is the remaining here is the viscous term here, okay, mu times d square u dy square. Okay, this is the term that is the remaining for the x component. For the y component, left-hand side acceleration part is also equal to 0. And then what you have left here is for the gravity minus rho g, and then also minus dp dy is the remaining, but there is no viscous term left. Okay, and then lastly, for the z, what we have here is the 0 equals to minus dp dz. Okay, so this is really good. What we have left here is the, okay, let's go back to the original size. Okay, so this is going to be, we have three equations. One is the x, two is the y, and then three is for the z. Okay, so that is the that's a simplified Navier-Stokes equation, which eventually you have to solve. Okay. All right. So now what is the number 4? The next step is the let's identify the boundary condition. Okay, conditions. In this case, okay, I just say that once again. So this is the moving at the speed of the u. So in this case, okay, this is the direction of the y, and then it's the this point is h, this point is 0, right? So in fact, the okay, we can come back to the the something that we learned in the week 1. Okay, this is the no slip at the two solid boundary. Okay, this is the no slip at the solid boundaries. Okay, so this is giving you the u equals to okay, how about I put it here? Okay, the u of the y equals to 0. Okay, which is the bottom part. Is the this is not moving, and then u of the y equals to h is the moving at u. Okay, so this is a quick review here, but in fact, they both of them are still no slip. Okay, no slip doesn't mean fluid particle does not move. Okay, if those solid boundary itself is moving, in fact, they travel together with the moving solid boundary, right? So both of them are still no slip. Okay. So in this case, this is the both of them are no slip. Okay, and then for the top surface is the okay, this is the bottom surface is the stationary. And then this is the moving. Okay, but regardless, the both cases they are both of them are the no slip conditions. Right. So this is great. This we have identified the boundary conditions. So I think we are really ready to solve the Navier-Stokes equations for the first time, perhaps in your life. Okay, so let's do this. Okay, number 5, solve the differential equation. At this point, this is really the math. Okay, this is the last part is really the mathematics here. Okay, so first part, in fact, after solving differential Navier-Stokes equations, you are able to have two information. One is the velocity, another one is the pressure. Okay, so let's first find this. The part A is the velocity. To find the velocity, let's just just use the number 1 equation number 1, which is the 0 equals to mu times the d square u dy square. Okay, so here's the let's try to solve this. Okay, we are going to solve this. In this case, okay, first things you have to know, this is a PDE, but we can make a very intelligent observation here, which is the it's subtle, but it's very important. All right. So because since u equals to u of the y, okay, in this case, originally, originally you can have four different variables x, y, z, and t. Therefore, we write it in the partial form, right? But in fact, because u has only one variables. So this is the PDE partial differential equation can be indeed an ODE. Okay, so this is we can just consider this ddy partial can be read as the regular ddy. Okay, so this argument allows us to solve the differential equation. Okay, so okay, this is very important. It's a bit subtle, but you have to have this thinking to solve the differential equation, right? So what we have here is the this equation number one is now considered 0 equals to mu of d square u dy square. And then with this this is now it is possible just to solve this, okay? And then this is the equivalently, okay, you can just divide both sides since mu is non-zero. This equation can be 0 equals to d square u dy square. Okay, so from here, let's just integrate with y. Okay, so first integration is going to give you this 0 equals to du dy. Okay, we integrated once, and then second derivative become the first derivative, and then but this is going to give you some integration constant. Okay, let's do it once again. And this is the once again, it's going to be okay. Du dy is going to be read as the after second integration. It's going to be u, and then this is going to be a y plus b. Okay, this is the second integration. Okay, so the integrate with y again. Right, so this is really we did integrate twice, okay, and then here a b is the integration constant, and then the what we want to do is we would like to know a and b by using the boundary condition. Okay, so this is the apply the boundary condition, apply the boundary conditions. If you remember, okay, first boundary condition is the u of the y equals to 0, which is the is going to be 0, right? So what you have left here is the 0 equals to, okay, if you plug in 0, okay, y equal to 0, u is 0, and then plus this a times 0 plus b. Okay, that's the first equation. Second boundary condition here is the y equals to h. You have a particular this speed of the u, which is moving along. Okay, so left hand side, okay, this is 0 equals to u is going to be capital U at y equals to h, and then this is going to be plus a times h plus b. Right. So now we are able to just solve a and b. A perhaps okay. Let me write it down here. So for a b, what we have left here is the we know immediately b equals to 0, and then that also gives you a equals to minus u over h. Okay. Oh, this is great. So now the Now, overall, we can just write it. Okay, overall here is the what we have here is the 0 equals to u. Sorry, this is the lowercase u. The function of the velocity u is equals to minus u over h times y plus b, but the b equals to 0. Then this is going to be lowercase u equals to this is the u over h times y. Okay, this is great. And then in fact, this is really telling you something amazing, right? This is really telling you, in fact, the u depends on y linearly. Okay, linearly. Okay. And then this is the also tells you velocity gradients of Couette flow is a linear. Okay, velocity gradient of the Couette flow is linear. So this is great. So in week one, I mentioned that the velocity gradient of the Couette flow is the okay. Let's just assume this is linear. But today, what we just did here is the by solving Navier-Stokes equation, we successfully find out the velocity gradient is in fact linear. So this is great. Okay. So that's the first part. The first part is the solving for the velocity. So second part is the let's solve for the pressure. Okay. So we can use the in this case equation number 2 and number 3. Okay. Let me just rewrite here. We have a two equation. One equation is the E0 equals to minus rho g minus dpd ey. And then second example here is the second equation is the dp dz, right? So this is the equation number 2. This is equation number 3. So let's try to solve. Okay, let's try to solve this. The differential equation. Okay, so here's the things. Okay, so let's say in most general, p is a function of the four variables, right? I mean, this is the same as the velocity here, right? Pressure may depends on the x, y, z, and t. Okay, but we are able to simplify this further because the first of all, okay, this is we can say first condition we consider is the flow is steady. Or we said flow is steady, but this is really the same as the flow entire system or entire the space is steady, right? So this is also really tells the p doesn't no time dependence for the for pressure. Okay, so this is really tells you there is no time difference here, dependence here. Another condition we consider is the okay. We also said the no pressure gradient in x. Okay, so this is really means this dp dx equals to 0. Okay, so actually here we need to think about what this means mathematically. Okay, this if partial derivative of the p with respect to x is equal to 0, right? The meaning here is the really p does not depends on x. Okay, So this is also telling you it doesn't depend on x. Okay, and then in fact, we also want to consider one last condition from the equation 3 above here, right? This is telling you dp dz is also equal to 0. Okay, dp dz equals to 0. So meaning here is the p does not depend on the z, right? So this is great. In fact, this argument really tells you originally when we started p, we may thought p may depends on the different variables, right? For different potentially for different variables, but this argument flow is steady, and then there's no pressure gradient in x, and then one of the result of the Navier-Stokes equation really tells you, in fact, p only depends on one variables, which is the p of the y. So once we have this, right, this is really good. This is really good. The argument is the same. Okay. In fact, the dp this is the for the p, right? In fact, okay. So this argument is really telling you we have this dp dy. Originally, it's a partial pde can be considered as the as an ODE, which is the dp dy. Okay, so this helps. Okay, this really helps. Okay, so the equation number 2 is going to give you this is the okay, let me just rewrite everything. This is 0 equals to minus rho g minus dp dy, and then the argument really tells this one is the ODE, I mean, or the regular derivative. This one equals to dp of the dy. So this allows us to solve it. Okay, this allows us to solve it. In fact, this is going to be dp dy equals to minus rho g, and then this is going to be, if you integrate. Okay, let me just put it down. If you integrate this, what we have here, integrate with y. Okay, what we have here is going to be p equals to minus rho g y plus some integration constant. Okay, so this is nice. Okay, so indeed, this is the this is how far we can get, but we can still do a bit of the interpretation here, right? Okay, this the when you want to have a pressure, okay, this is the EU, and then this is the bottom surface, right? So in fact, if we want to know the pressure, the pressure between here, okay, this is the pressure depends on the elevation y. Okay, one thing that we can understand here is the p varies with the p varies with the y. If you go higher, okay, this is the uh it's actually varies with respect to the log here, and then the another things you can say here is okay, we don't know the value of c. C is not determined. We just need boundary conditions. Need boundary conditions for the pressure. Okay, so but at this point, we don't know. This is the in fact, this c is coming from the integration constant, right? This is the some constant, which cannot be identified with the given information in this particular problems here. Okay, but it's really the what happens here is um the pressure varies between these two walls with this is also linearly. Okay, so P varies with Y. This is the linearly. Okay. All right. So that's really the same. Okay. So well, if I make one additional comment here, in fact, this one, this P equals to one last comment here is this P equals to minus rho G Y plus C. And then this one is nothing but the same as the minus gamma Y plus C, right? And then we can also, if we just want to take a derivative here, then this is the dp dy equals to minus gamma. Then if you remember this, right? This particular equation is the same as the hydrostatic equation. Okay, so that's what we learned in the week 2. Okay, so what we really had here is that in fact, uh, so because there's no flow between in the y direction, this is if you want to solve for pressure, eventually this expression, the equation is going to be reduced to the hydrostatic equation that we identified in the week 2. It's the same here, right? So that's really great. Okay, so let me just summarize what we have here. So in summary, it's a bit long. This is the any Navier-Stokes equation problem. This is the long. Okay, this is the super long. So in summary, what after doing the calculation, we find here this is velocity fields. What we have here is this velocity is we only have only y component uy, which is identified as u over h times y in the direction I. Pressure field is this pressure equals to minus rho g y plus some constant, right? For Couette flow. Right, so this is great. And then just for the if you really want to revisit the shear stress, okay, this is just a revisit shear stress. It's a quick comment here, okay. Shear stress is this tau equals to mu times du dy. Okay, so in this particular case, okay, in this particular case, if you go here, in this case, okay, where the u of the y equals to u of the y equals to u over h times y. Okay, so this is going to be this is telling you du dy is nothing but u over h, right? So this is going to be this equals to okay we have this relationship, and then this can be applied here. And then what we have here is the mu times u over h. And then this one is the same results as those discussed in week 1. Okay, so this is the really, the what we proposed, or what we just assume in the week 1 is not, the not something, the too random. We are able to actually prove this back by using the Navier-Stokes equations. Okay. So this is going to conclude the all those derivation of the and then working for the Couette flow.